Hello, I'm Schwa, and if you let me, I'd love to be your math teacher. Welcome to the second episode of this series where I teach math, I guess, from hopefully a deep perspective, but still assuming mostly no background knowledge. Now, if there's any mathematicians watching in the audience, you will probably see this set theory and think, oh my goodness, are you out of your mind? You can't teach set theory as the first thing you teach. But I'm a little crazy, so I'll give it a go. You know, set theory is a very deep subject, and I will try to introduce you to some of the more interesting details, or the, deeper things too. But of course, the main emphasis is on understanding, the high level idea that in mathematics we can technically construct everything using sets, and sets are very fundamental, and we use sets in mathematics all the time, right? That's basically the takeaway here. So if you don't remember anything else from this episode, then just remember that sets are ubiquitous. So that means they are everywhere. Ubiquitous. Okay, this is cringe because I probably didn't spell this right, but whatever, I'm a mathematician, not an English major. Okay, so sets are ubiquitous, and they are, or they can be, and, well, in parentheses, are the building blocks of mathematics. Building blocks of math. Building blocks of math. Excuse my handwriting. Yes. So, as I said in the introductory episode, I always find it helpful to draw or to illustrate mathematical ideas with some sort of concrete visuals. It might be something from the real world, or it might be something slightly abstract, but, something that is a little concrete. So, what I shall do is I will try to illustrate sets as things that you can put other things in. So they're like little packages or stuff like that. So maybe I should move a little bit, get myself some more space. So we can have something, right? And then we can have little things inside of it. What should we put in there? Let's put little dots inside of it. And the container is called a set that the dots are in. And the container, let's say the set is called A. Now, usually when we name sets, we usually use capital letters. So this capital A is used to denote the fact that it's the name of this set, right? It's a single capital letter. Usually that's the way we name sets in mathematics. Now these dots, they're inside the set. So, imagine that this is, what could that be? Like a sack of marbles or something, or a bag of marbles. And these marbles inside the bag, right? So this is a marble bag. So the marbles are called elements of the set, right? And if a marble is inside a bag, then we have specific mathematical notation to denote that. So let's say that this marble right here, it's called element, what should it be? Element, do I want to use the name X? Because the name X is a little special in mathematics. You know, some people might get some PTSD almost if I call it X, but let's call it X. So usually when we name these marbles inside the set, we use lowercase letters. So uppercase letters for the container and lowercase letters for the marbles or whatever you have inside the container. Now, the fact that this X, this marble, is inside the bag, the way we write that in mathematics is with this symbol. So it kind of looks like a euro. It's like you curve it and then you have this. Maybe it's familiar notation, maybe not. Who knows? But this is how you denote that X belongs to the set A. So you first write the name of the marble, then this belongs symbol, then the name of the set. So X is an A. And maybe this element right here could be Y, and this element right here could be Z. And then we can also write, these are all true statements, we can write that Y is an A, and we can write that Z is an A. Perfect. So we have formed 3 true statements about this set A, right? Now, are there any, what are these marbles? I mean, I call them marbles, but of course in math, you know, usually we deal with numbers, so maybe you might expect, oh, are these numbers, perhaps? Now, listen, this is where stuff gets a little subtle. This is like the basics, or the very, very basics of set theory. This is, you know, this marble and bag idea. Maybe I should call it naive set theory. And I'm not trying to be mean. This is an actual term that that mathematicians use. Naive. Sorry, what am I writing here? I need my eraser. Okay. So naive set theory. Naive set theory. Like that. And what do we mean when we say naive set theory? Well, when mathematicians say naive set theory, they basically mean to say that let's not worry about a formal treatment of set theory, because I acknowledge that set theory can be very difficult. So let's just think about bags and marbles, and those marbles, for the most part, they can be anything, right? That's naive set theory. So naive set theory is saying, you know what, let's not worry about set theory, basically. Now, what does that mean? Like, is there something more to set theory, more than these marbles? Well, let's get to that in a second. But first, let's think about, from the point of view of naive set theory, you know, I want to emphasize that there's no reason to restrict what we could have inside this set, right? So this is all in the realm of naive set theory, and usually it's okay to, I guess, be a little naive and just assume that everything works the way it does without fancy formal mathematical axioms and stuff like that. So usually you can put anything you want inside these sets that we have, right? So for example, let's define a new set B. So set B, and this set B is gonna contain all the towns and cities of the world, right? So the set B, and once again I'm gonna illustrate it as this sort of bag, right? Now, what am I gonna put in the bag? Well, I'm gonna put different cities and towns inside the bag, right? So, for example, we're gonna have San Francisco. That's a city. San Francisco. I don't know how to spell it. And then what other cities are there? Well, there's California. These are American cities. Then in Finland, there's Helsinki. That's a good city. Yeah, and I'm not going to list all the cities, but the set B, that's the set of all cities in the world. Now, what can we do with sets? Well, we could define a new set. So we could define set C that is the set of all capital cities in the world. So that's going to include Helsinki because it's the capital of Finland. I could list a lot of European capitals because I'm European. But I think Washington, D.C. That's the capital of the United States, I believe, and the capital of Australia. It's not Sydney. I think it's Canberra. You know, if I'm getting these wrong, please excuse me. It's geography. It was never my strong suit. But here we have capitals, right? So we formed a set inside which we put capitals. And then here we formed a set where we put just cities in general. Right? Now, what we might notice is that each capital is a city, but not every city is a capital. So, for example, Canberra, that's a city, but California, that's not a capital, right? So, in this case, one way that it's common to illustrate this is that we draw set B here, and this is the set of all cities, and then we draw the set C here inside B, and this set C is the set of all capitals, and the set of all capitals is inside, it's contained within this bigger set of all cities, right? And this diagram right here is known as a Venn diagram. Venn diagram. And Venn diagrams are very, 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 very helpful in, I guess, naive set theory especially. And whenever we have this, whenever we have a set completely contained within some other set, which is to say that every element of this set is also an element of this set, then we say that C is a subset of of B, right? C is a subset of B. Just like that. Okay? And there's a way to write this down mathematically, right? Just like how there was, we could say that X was in B. We had this this symbol that denotes that X is a member of B. We also have notation to say that C is a subset of B. And the way that we write that is by writing C and then this symbol. C is a subset of B. Now, there's a little bit of disagreement here as to how this should be denoted. So, you're probably familiar with the less than or equal to operation or relation, as it turns out it is. For example, we can say that 3 is less than 5. But we can also say that 3 is less than or equal to 5. And we often say that 3 is strictly less than 5 whenever the equality is not included here. So similarly with sets, a lot of people say that this notation means strict inclusion. So C is strictly contained in B, but it's not equal to B. Whereas if you write C is C is a subset of B with this equality, then it is possible that C could also be equal to B, which would mean that every city in the world is a capital, right? Now, not all people use this convention, so some people will say that these two mean the same thing. I personally prefer to have this difference here, and usually the people that do say that these are the same thing, sometimes people might write C is strictly contained in B, right? So they will. I don't know how easy that is to see, but they will write this containment symbol and then cross out the equality like this. So they will write this, and this is to emphasize that they cannot be equal. So generally, these two mean the same thing, and generally, or to me, these two mean the same thing. But for some people, these two mean the same thing. So there's a bit of ambiguity with the notation, right? But that's just a matter of preference, right? So for simplicity, I recommend treating inclusion the same way that you would treat comparison. So if 3 is less than 5, then 3 cannot be equal to 5. So for example, 3 is less than 3. That would be false, right? But 3 is less than or equal to 3. That would be true, right? So I recommend sticking with a similar convention here. But of course, that's up to you. Okay, so I've covered sets. Sets can have members. Subsets are basically sets where every element of the subset is also an element, but also belongs to the potentially bigger set. So my example was these bags of marbles, where the marbles in this case are cities, right? And usually it is very characteristic of naive set theory to, assume that these marbles, they can be anything. And any set that seems reasonable is in fact reasonable and exists, and we can work with it, etc. And generally, that's an okay approach. That it works. And even serious mathematicians don't usually think much deeper than that, right? Now there's some additional if you take a course on set theory, an introductory course to mathematics, then we will also find some elementary set operations, right? So for example, right, so let's let's take the first example with numbers. So if we have the set A, okay, let's not do that yet. So we have the set A, we have the set A here, and the set A contains the numbers 1, 2, and 3, and then the set B contains the numbers 2 and 5. Now we say that the union of these two sets is is a set containing elements from both of these sets. Or sorry, let's be very careful here. So the union A union B, so we denote it with this sort of U-looking symbol. It's called a cup, I think, at least in LaTeX, which is a program for writing math. So A union B is a set where every element of that set either belongs to A or B, or potentially both. So 1 belongs to A, so 1 belongs here, and 2 belongs to A, so 2 belongs here, 3 belongs here, and then 2, well, with sets, we usually don't write duplicates, because when it comes to sets, the only thing that matters is whether an element belongs to the set or not. Like it doesn't matter whether the set has some value several times. That's not a thing, right? So we don't have to write 2 twice here. And then 5, that's also part of the set because it belongs in B, and any other element that we might think of certainly won't be an element of either of these, so it also won't be in here. Okay, this is called the union of two sets. And then we also have an intersection, and honestly, like, you don't need to remember this, but I'm just putting this out there. I'm just putting this out there to illustrate that there are these set operations, and eventually, maybe they'll prove to be useful to us. But I'm just introducing them. You don't have to remember these perfectly right now. So the intersection, that's a new set where every element has to be a part of both of these sets. So it's not enough that it belongs to one of them, it actually has to belong to both. So 1 belongs to A, but it does not belong to B, so that's not going to work. 2, it's in A, but it's also in B. That's nice. Okay, so we get 2 in here, but 3, on the other hand, well, it's not in B, so no can do. And we can illustrate these two operations using Venn diagrams. So the Venn diagrams that we covered earlier, somewhere in there, it's still in there actually. Those we can use to illustrate what unions and intersections are. If we have a set A and a set B, right? So this is B, this is A, and they might have some overlap. The interpretation here is that any elements in here belong to both sets, any elements in here belong only to A, and any elements in here belong only to B. So let's have the setup twice, right? And the union of these sets, well, it's any element that belongs to both of the sets. Now maybe we should have these sets inside like a box that we could call the universe, right? So often with Venn diagrams, the sets are inside a rectangle, and the rectangle might be a set called X, or it might be called, I don't think that's going to show on camera. Ooh, that's annoying. So this outer rectangle is often called X, or the universe. So it's like every possible marble, I guess. It's one big bag that encapsulates all the marbles we could wish for, right? But the idea of a universe in set theory, it's a little difficult, a little controversial too. We'll maybe get to that later. But in Venn diagrams, in naive set theory, it's a useful idea. And the idea of a universe, it allows you to define also this new set theoretic operation called the complement of a set. But again, let's not get ahead of ourselves. So the union of two sets, well, it's any element. It's not any element in here, right, outside of the bags A and B, because it needs to, any marble needs to belong to at least one of these sets. So this is okay because it belongs to B, and I guess this is okay too because it also belongs to B. And let's see, well, this is also okay because it belongs to A. So this is the union where it suffices that a marble belongs to at least one of the sets. But outside of A and B, that's not a part of our union. Here we have the intersection, which I will write. So the union was written with the cup A, cup B, and this is A intersection B. So the cup is rotated on its on its head like that. Okay. So here, these elements in here, well, they don't belong to A. These belong to both. That's good. But here, these elements don't belong to B. So those are not a part of the intersection. So the intersection here is only this overlap between the two bags, right? Okay, elementary, naive set theory, almost basically done. There's a third operation that we could define called set. Is it set difference or set minus? It's probably set difference, maybe. I don't know. But again, like, I don't want to overwhelm you with all the different set operations and stuff like that, because I feel like that's not really the point here. We're not gonna need these for a while, probably. So yeah, maybe let's just move on to some more philosophical stuff, right? So this was naive set theory. But like, let's see if there's any issues with this idea that these marbles can be anything, that you can just put anything inside a bag and call it a set, and there you go. So let's think about this. Actually, before we jump off the deep end, I'll introduce once again some mathematical notation, unfortunately. So generally, the way that we write sets is, instead of drawing the bag and putting in some marbles like 1, 2, and 3, right? We instead, and this would be the set A, instead of doing that, we could write the name of the set equals, and then open up curly braces, and then list out, separated by commas, the elements of the set, right? And this kind of makes sense. You usually use parentheses to group certain things together to form like a single sort of package. And here we just use curly braces to form a single package called the set A, right? And it contains the elements 1, 2, and 3. Wonderful. Okay. Now, okay, now we can get to the real stuff, or to the very philosophically interesting stuff regarding sets. If I define a very weird set, is that going to be a set? Let's think about this. So I would like to define the set B as a package where inside the package I put another package, and inside that package I put yet another package, and inside that package I put yet another package, and so on infinitely. So this is infinite recursion over here, is what I'm trying to construct. Infinite recursion. Is this object B, is that a set? And using naive set theory, where everything is just a marble and you can put things into bags like this, it's hard to say. I mean, there's infinity involved. Maybe that's a little scary, but maybe this is just some well-defined object. Maybe it will be okay. It turns out that according to at least most of the widely accepted axiomatic frameworks for set theory, this is not allowed, right? Now, if you don't know what axioms are and stuff like that, don't worry. We'll maybe probably get to that at some point in the series. But basically, if we're being careful, so if we think about this really carefully, then this is not allowed, right? Not allowed. Now, how could we intuitively sort of think about why this might not be allowed, right? Why is this a problem? Well, I don't know if you've heard of Russell's paradox, but I'll introduce you to Russell's paradox. It's a very, very funny, very quirky thing. There was this guy called Bertrand Russell. I don't know when he lived. I don't know much about him, actually, because I am not a historian. I'm sorry. But we have Russell's paradox, right? Russell's paradox. Okay. And the idea behind Russell's paradox is that we construct a set that sounds like it should exist, but it actually does not exist, or there's a paradox, right? And you'll see in just a moment what the paradox is, what the problem is. Let's take a look, right? So let's consider a set that contains all the sets that don't contain themselves. Okay, that's really weird, really scary. But let's think about this. So, for example, the set containing 1 and 2 does not contain itself, because a set that contains this set could, for example, we could have a set that contains this set and then the number 3. So this set right here contains this set, but this set does not contain itself, right? So to be a little more specific, if we define this as A and this is B, then we can say that A is inside the container B, but however, A is not contained within itself, right? So, you know, according to naive set theory, or you know, if we're not careful about what a set is allowed to be, then we could define a set. So let's define C as a set where it's every set that does not contain itself. Sets that don't contain themselves. Sets that don't contain themselves. Don't contain. Contain themselves. Themselves. Right? Okay, now let's think about whether C contains itself. So let's do this on a case by case basis. So in the first case, if it is so that C is a member of itself, then that would mean that C contains itself, but we define C to be the set of sets that don't contain themselves. So this is an obvious contradiction, right? That's not what C is. Contradiction, not what C is. Not what C is. Okay. Now, what about case 2? Case 2. So in case 2, we say that C is not a member of C. And notice, like, these are the only possible scenarios. Like, either C is a member of C, or it's not a member of C, right? There's no other option, conceivably. Either it is not a member or it is a member, right? So let's see. So maybe it is not a member of C. But if C is not a member of C, then it does not contain itself. So in that case, the definition says that C contains itself, right? Because C is the set of sets that don't contain themselves. So if C doesn't contain themselves, then the definition says that C is a member of C. But that's a contradiction, because we assumed that C is not a member of C. So that's a contradiction. So we notice that this seemingly innocent definition of sets that don't contain themselves, right, actually yields a situation where, regardless of whether C is or is not a member of that set, we always find a contradiction. So realistically, this set is crazy. We should not be having this set because it leads to a contradiction. Mathematicians don't like contradictions because contradictions can be used to prove anything, basically. So this is not good. So this Russell's paradox was what originally motivated mathematicians to move away from naive set theory into more rigorous, formal, axiomatic footing. And that's like modern set theory. So to combat this paradox, to combat Russell's paradox, lots of different like axiomatic frameworks have been proposed, like ways to like basically dictate, like, okay, this is a set, that's okay, but this is not a set, that's not okay, right? That's the problem, like, which sets are allowed, which sets are not allowed, right? One solution to that is ZFC axioms, right? And they're called Zermelo-Fraenkel set theory with an additional axiom called the axiom of choice. So the C stands for the axiom of choice. With the axiom of choice. And now, you don't need to remember this, right? And you don't need to know what the ZFC axioms are. But what I'm saying is that whenever we really want to define what sets are and be free from paradoxes and, that sort of thing, then we can list out axioms that sets must satisfy. And one way to do that is with the ZFC axioms. And, I'm not a set theorist or like a logician or anything like that. But basically the trick that we do with at least ZFC is that instead of allowing like arbitrary sets, basically, you allow some very simple sets. Like, for example, the empty set. That's certainly a reasonable set. By the way, that's often denoted like this, right? So the empty set, that's a reasonable set. And then maybe we can build on that to build some other set. Hold on. Like this, I guess. And then we can have this, right? Okay, this is probably just scribbles, if you don't know what I'm doing here. But basically, we have these simple sets. Based on them, we can make new sets, and then we can basically, by a certain rule, we can rule out some elements from an already well-established set to form a new set. And that way, we can, in a very regulated fashion, form sets that don't break any rules, right? So, yeah, basically, the idea is that we start off with some sets that are fine, and then we let people manipulate those sets in very particular ways that allow people lots of freedom to do kind of whatever they want, but still not too much freedom to so that there will be any paradoxes. Now, the interesting thing is that, strictly speaking, we actually cannot know whether there are any paradoxes or not, right? So, it's easy to come up with a set theory where there is a contradiction, like Russell's paradox, right? If you allow sets to be infinitely nested within themselves, then you get Russell's paradox, and that's not good. But we actually don't know whether the current foundation of mathematics, whether ZFC contains any such, paradoxes or contradictions like that. Like, it could be that one day we find, a situation comparable to Russell's paradox inside ZFC, which is what we use to ultimately build up mathematics from the ground up. So it's possible that mathematics, at a very fundamental level, or at least the way that we've constructed it, is what's called inconsistent. So it kind of just doesn't make any sense. That's possible. However, people who have, thought about this, they all tend to think that that's very unlikely because the ZFC axioms are, in some sense, very good. Also, there's there's a lot of redundancy in the axioms, or at least some redundancy. Like some of the axioms could be dropped out and you can still build like a lot of mathematics. So yeah, but that's interesting. And that's one of the, if you've ever heard of Gödel's, I don't know how to pronounce it, but Gödel's incompleteness theorems, then it's one of them. It's one of them, which states something that any sufficiently complicated axiomatic system cannot be used to prove its own consistency or something like that. And it basically means that there could be some hidden contradiction lurking around in our mathematical framework. And if someone were to find that, then they could prove any theorem they could ever want. I mean, it would render mathematics kind of useless, or at least that framework kind of useless, but you could prove anything you wanted very easily. So, for example, Riemann hypothesis, which is considered to be one of the hardest problems in mathematics, that could be proved among any other statement if you found a contradiction in ZFC. But realistically, that's probably never going to happen. But philosophically, I think that's quite interesting. And, you know, we're never going to know whether such a contradiction exists within ZFC until you find it, which is probably never. So realistically, we're probably never going to know. But yes, I think that's interesting. That's a lot. Okay, what's the big takeaway here? Okay, maybe I'll still add one more thing, right? So what's the reason for all of this? So or what do I mean when I say that set theory is used to build up all of mathematics? That's what I said, right? What do I mean by that? In mathematics, there's this funny interplay, this dance again, between the constructions, the logical things that we can make, right? So a set, and then these abstract high-level ideas like, you know, names of cities or natural numbers. You know, we can arbitrarily decide to give this empty set the meaning 0, right? So it corresponds in some sense to 0. And then this set that contains the empty set, we could call that 1. And then we could call a set that contains this 1 and also every element of this set, so the empty set, we could call this 2, right? And so on. And we could, using sets, we could construct these new sets according to ZFC, or we could use ZFC to confirm that these are in fact valid sets that should not lead to contradictions. And we can call these different sets natural numbers, right? And then we have a formal basis for what these numbers are, because we could say that, you know, 1, it's just this set. 2, it's just this set. And what's the importance of that? Well, it would be kind of cumbersome to just posit the existence of these numbers, like, number 2, you know, it exists somewhere out there. You know, that's kind of weird. But if you just posit that a set exists and they obey some rules, then maybe that's less weird. Maybe you can generalize that thinking to more things than just numbers. And in that way, maybe numbers can be just one part of some bigger logical Lego construction that we make. I don't know. But in any case, we often technically use sets to define the natural numbers. However, it's important to note that in practice, when we do math, we absolutely don't think of these sets, But so it's kind of like how matter is made up of atoms. So if you have a chair that's made up of atoms, but when you actually sit on the chair, you don't think about the atoms. So that's kind of the same thing here. These are the fundamental building blocks of our numbers, but when we actually work with the numbers, we don't need to be aware of how specifically they're constructed from smaller parts. But these sets are very elegant, very beautiful smaller parts from which you can construct these beautiful abstract entities. And I guess one question you might have, I mean, frankly, you probably weren't even paying much attention to the details of this, of these sets, like what these are. But these are called von Neumann ordinals, right? That's what they're called if you want to look them up. Ordinals. And a question that you might have, of course, is, well, wouldn't it be simpler to just define 0 as the empty set and then put an empty set inside that and call that 1 and put another empty set inside that and call that 2, right? Wouldn't this be simpler than whatever this is? And if it's not clear what this is, you can look these up on Wikipedia, right? But this has the nested empty sets thing, which created the Russel paradox, right? So and that's why we can't do this. So we have to have a slightly more cumbersome construction. And one of those constructions is the von Neumann ordinals. But anyway, remember that I started all of this with the question, it's somewhere over here. Yeah, so the initial question was whether this set right here is a valid set or not. And I said it's not. And this is related to Russell's paradox somehow. But what is that? What is that connection, right? So let me just that's where I think I'm going to finish off, right? So Russell's paradox says that it's about considering, sets that contain or maybe don't contain themselves, right? Now, let's see. How could we construct a set that contains itself? Well, does the empty set contain itself? Well, no, because it contains nothing, so certainly it does not contain itself. But if it were to contain, but the simplest set that contains the empty set, presumably, so let's call this A. So the simplest set that contains the empty set is presumably B, which is just the set that contains A, right? Right? Now, does this set contain itself? Well, it contains the empty set, but it does not contain a set that contains the empty set. So a simplest set that contains B is maybe C, which is just set that contains B, right? That's the simplest set that contains B. But B, of course, was a set that contains A, and A was the empty set. So this is a set that contains the empty set, right? And this is very cumbersome to read. Basically, we notice that as we want the set to be contained within another set, and we take the simplest set that can do that, we form this like chain of sets where it just keeps diving in, like there's sets inside sets inside sets inside sets, right? And if we keep doing this, then we get exactly precisely the thing that I asked, like, is that a set or not, right? And it's not a set, because this set, like if it were a thing, well, that's basically what Russell's paradox is kind of after, right? It's a set that contains itself. Or, if you have a set that contains things that don't contain themselves, right, that situation easily starts to look like this, and this in particular is not a set. Okay, maybe that was not so clear, but I don't know. Maybe that's food for thought. But let me end by giving you the central ideas here. So sets are basically containers, and naive set theory says put anything in them, even cities, even stuff. It doesn't matter, right? So naive set theory says put anything in there, and more axiomatic modern set theory might say, okay, let's be a little careful about what's a set and what's not. These sets, they're named in capital letters, right? Uppercase letters. Also, they have operations. So there's the union of two sets that forms a new set, and there's the intersection of two sets that also forms a new set. So there's operations between them, and they are the building blocks of mathematics in the sense that we can, strictly speaking, we can define the natural numbers. I never said what the natural numbers are. But, we can build the natural numbers using sets, and the natural numbers, of course, that's 0, 1, 2, 3, 4, 5, and so on. So the natural numbers are basically numbers that you can use to count things, right? So they are essentially the beginning of what is actually a very long, chain of thought and argumentation in how to construct, integers and rational numbers, real numbers. Natural numbers is where the story begins. And I think in the next episode, we're probably going to start thinking about what different numbers are, right? Alternatively, I could maybe link to another Roof's video because he does a very good job at explaining things. Natural numbers is where the story kind of begins. And something a little controversial about the natural numbers is whether 0 is a natural number. But if you ask me, then absolutely. I think most modern mathematicians consider 0 to be a natural number. And the reason for that is because it's kind of like the integers are defined in terms of the natural numbers, and then adding in 0 as kind of an afterthought is a little cumbersome. In terms of constructing the numbers that we're used to set theoretically, it's much cleaner to include 0 as a natural number, because why wouldn't you? Well, like with the von Neumann ordinals, it doesn't really matter. You might as well define 0 as well. Of course, then you might ask, well, why not also define -1, -2, stuff like that. But the reason is that you want to define addition of natural numbers, and that actually does not become any harder if you add 0. Right, because 0 is a very easy number to work with. But with negative numbers, you have to be a little bit careful about how you do that. But anyway, that's a story for another time, right? So I think that's where I'm going to end the story here. Thank you all for listening. That's set theory. It's the foundation of mathematics. This was a little abstract maybe, but we're going to get to some more concrete, maybe some more interesting stuff as well in the future. So I hope you'll stick around, and thanks for watching. Keep at it, and I'll see you next time. Goodbye.